So welcome to the third lecture of the digital image processing course. In this lecture, I will talk about some approaches for histogram processing and contrast enhancement, as well as I will give you some introduction onto fundamentals of spatial filtering. So the topics that will be covered in this lecture are histogram processing in general, then histogram equalization and histogram matching. Finally, a little bit on local histogram processing. Then I will introduce you to the fundamentals of spatial filtering, do a quick comparison between correlation versus convolution, and then finally concept related to separable kernel filters. So let's just quickly go over the definition of histogram one more time. We have introduced this previously in a previous lecture. So let's just assume our subscript k for k from 0 to L minus 1 to represent the intensity values of an L level image f of x and y. So if you remember from before, we said that the number of level of intensities has a direct relationship with the number of bits that you use for representing an image. So for example, in an 8-bit image, we have 256 different levels of intensity ranging from 0 to 255. So based on this assumption, we can define the unnormalized histogram of image f using the following equation. H of r subscript k equals n of k for all the values of k, when n subscript k is the number of pixels of the image with the intensity r subscript k. So in effect, we create some histogram bins, basically the subdivisions of the intensity scale, and then we count the number of pixels that fall within those histogram bins. So the most straightforward way is to divide the L level image into L different histogram bins and then start counting all the pixels with a specific intensity value and then populate this unnormalized histogram. We can normalize this histogram by dividing the unnormalized histogram by the total number of pixels in the image. So if our image has m number of rows and n number of columns, as shown here, the normalized histogram, which we call it P of R of k, is defined like the equation. Basically the histogram, the unnormalized histogram, divided by the multiplication of m and n, which gives the total number of pixels within that image. So in some sense, you can think of this normalized histogram as the probability function that specifies the probability of any intensity values happening within the image. So since we have this other interpretation as well, we can use the concept from probability theory to quantify and find the properties of this probability distribution. So one of the very useful properties is that some of the probabilities over the full range of the possible values or possible possibilities will add up to 1, and it is something that you can easily verify by plugging the equation for the normalized histogram into this equation, and then if you do the summation, you realize that they add up to 1. So as I said, the components of this function are the probabilities of intensity levels in the image. So usually when we use histogram, we are dealing with two types of images. Either the image is low contrast or high contrast. So in low contrast images, the histogram has a very narrow intensity range, and that is in general. On the other hand, high contrast image has a much broader intensity range. So now the question becomes how we can enhance the contrast of an image, since generally speaking, a more even distribution of the histogram is linked to higher contrast. So it is very natural to assume that if a histogram is expanded to cover the full range of intensities, the contrast is going to be improved. In an ideal image, you can say every intensity level corresponds to the same number of pixels. So the concept of histogram equalization works based on this uh, assumption. So here we have four different images of the same scene, but with some problems with regard to the histogram. So the first one, the image is relatively dark, and as you can see in the histogram of the image, all the intensity values are located in the lower half of the intensity range, and that results in a very generally dark image. The second image, we have a much brighter appearance, but the image looks very washed out. So if you look at the histogram of the image, you see that now the intensity levels are more located toward the bright side of the intensity range. We have this image of a low contrast representation of the same scene, and you can see here again we have another type of uh, very narrow representation of the intensity levels. And finally we have this high contrast image, and as you can see the histogram is much more spread out across the full range of the intensity values. So the aim is to uh, start from any of these three low contrast images and create an image that resembles more of a high contrast histogram. Histogram equalization technique uh, fall usually under the umbrella of single pixel transformation that we introduce later. So to begin with, we can just assume a continuous case since the concept of histogram equalization can be mathematically proven in a continuous case. It's not the same for a discrete case, as you will see in later slides. So let's just assume we have a continuous range of intensity values. We represent it with R, and the range is anywhere from 0 to L minus 1. And let's just have a transformation or intensity mapping function defined in this form. S equals T of R being the input intensity range and S being the output intensity range. So we defined some conditions on function T. So one of them is that function T needs to be a monotonically increasing function in the interval of 0 and L minus 1. And the other condition B, is that the range of the values that this function produces should be exactly the same range as the range of input. So as you can see, T of R lies between 0 and L minus 1 for any R which is between 0 and L minus 1. So this is an example of a monotonically increasing function. So in different parts of this function we have different properties. So for example, in this part and in this part, as you can see, it is strictly monotonic, which means that there is a one-to-one correspondence between any pixel with the input intensity range and the output intensity range. So in these two regions, the correspondence is one-to-one and is reversible. But there are some ranges of values that you have mapping of multiple intensity range to one single output range. So since we have this, we have to define condition A prime, which is used for functions that are strictly monotonic, which means that the correspondence is going to be one-to-one and reversible. So these three conditions each guarantees some useful properties of the transformation function. Condition A guarantees that the output intensity values will never be less than the corresponding input values. That helps us to prevent artifacts and any intensity reversal. Condition B guarantees that the range of the output intensities is the same as the input image. And if you remember from the previous lecture, when I was talking about arithmetic operations done on images, I mentioned that when we do some processing on an image, it is possible that the range of the intensities in the final image is different than the range of the intensities in the input image, and to remedy that we used either clipping or scaling. So having condition B basically guarantees that we don't have that problem anymore. And condition A prime guarantees that the mapping function from R to S is one-to-one and reversible. So now that we have these conditions on the transformation function, let's just move forward with the continuous case of histogram equalization. So for this, let's just assume PR of R and PS of S being the probability distribution function, or PDFs, of the intensity values in the two images that we have, R being for the input image and S being for the output or the histogram equalized image. So from probability theory, which I don't go in much more detail here, if you are interested you can refer to the corresponding text for probability theory. We conclude that if the PDF of the input image and the transformation function, which satisfies the condition that I described previously, if these two are known, and if TR is a continuous and differentiable function over the range of values, then we can calculate the PDF of the transformed variable S. And the equation for that calculation is mentioned here. So PS of S equals PR of R multiplied by the absolute value of the differential of R with respect to S. Or more specifically, this is the inverse of differential of S with respect to R. So, but this is too general because we didn't specify any properties on the function, the transformation function. So for the purpose of histogram equalization, we want to have a PDF for the output image that resembles a uniform distribution over the intensity range. So let's just assume this more specific function as the transformation function and see if this function satisfies the requirement that we have for the output PDF. So here we define S to be L minus 1, which is a constant multiplied by the integral of the PDF of the input image over the range from 0 to R. And here we use this W parameter as the dummy integration variable. So this is generally called the cumulative distribution function, or CDF. So now that we have this, let's just see if we can find the probability distribution function of the output image. So before that, let's just see if this transformation function satisfies the conditions that we specified before. So the first condition that we had was the transformation function need to be monotonically increasing. So let's just see if this condition is satisfied. So first of all, in this function we have L minus 1, which is a positive number. So this doesn't have any effect on the function. Then we have this integral that is computed over the range from 0 and r. And then inside the integral we have the PDF of the input image. So as you know, PDFs are always positive, and if we are computing the integral, uh, since integral is the area under the function, since the PDF is always positive, this integral is going to be always increasing when we change the value of r from 0 to its final value, which is L minus 1. So this uh, transformation function that then satisfies the first condition that we had, condition A. This uh, transformation function satisfied that condition, but not necessarily condition A prime, because it is possible that uh, there are some, let's say, especially in the discrete case, we have some probability values that are 0, and even though we increase the range, uh, the output function does not increase. But I will talk more about this later on when I talk about the discrete case. So the other condition that we had was the range of the output intensities should be exactly the same as the range of input intensity. So to test that, we can just replace the value of r with the minimum and maximum value in the range. So if we have r to be 0, then we have integral from 0 to 0 of the PDF of the input image, which is going to be 0. So for value of r being 0, s becomes 0 as well. On the other hand, if we put r as the maximum value possible within the intensity range, which is L minus 1, then we have the integral from 0 to L minus 1 of the PDF of the input image. And as you remember from one previous slide, is that the integral of the probabilities over the entire range equals 1. So in that case, this part of the equation equals 1, and then the maximum value of s will be L minus 1. So as you can see, when we change the value of r from 0 to L minus 1, the value of s also changes from 0 to L minus 1. So this satisfies the condition, the two main conditions that we had for the transformation function. So now let's try to derive the PDF of s. To derive the PDF of s, first thing that we need to calculate is the derivative of s with respect to r. So this is pretty straightforward. D of s over d of r is going to be the derivative of the transformation function with respect to r. So in the function that we had this constant which we can take out of the derivative, and then we will have this constant multiplied by the derivative of this integral function with respect to r. And as you can see, and you know from mathematics courses, that the derivative of a function with respect to the variable r of an integral function, which is defined based on that variable, is going to be the function itself. So this derivative of the s with respect to r is simply L minus 1 multiplied by the PDF of r. So now that we have this, we can easily replace this derivative into the equation that we had for the PDF of s. So P of s, PS of s equals PR of r multiplied by the absolute value of the inverse of this derivative. So if I simply compute the inverse and replace it here, I will have PR of R multiplied by 1 over L minus 1 PR of R. Since all the values in this equation are positive, we don't have to have the absolute value, then the PS of S simplifies to 1 over L minus 1. And as you can see, this is a constant value, which means that the PDF of S will be a uniform distribution. So you can see the effect in this example. We have this random but continuous PDF for the input image that is spread over the full range of 0 and L minus 1, and after doing the equalization we end up with a uniform PDF for the output image. So let's just do a quick example of how this can work using a different function. So for this example, let's just assume PR of R to be 2R over L minus 1 squared for the range of R being from 0 to L minus 1 and 0 everywhere else. Again, we can create the transformation function using the equation that we had before, which was L minus 1, the integral of PR of R from 0 to R. And here we use W as the integration variable. So if I replace this function within this range inside the integral, this 2 value, since it's a constant, you can take it out of the integral. Also this L minus 1 squared, since it's a constant, you can take out. And one of L minus 1 and L minus 1 squared, one term will be cancelled out, so the constant outside is going to be 2 over L minus 1. So now if we compute the integral of W dW, it's going to be W squared over 2. So if I replace the value of R in that equation, I get R squared over 2. And then if I replace W with 0, I get 0. So after all the calculation, this is the transformation function that we will have, R squared over L minus 1. So now let's just compute the derivative of this function with respect to R. The derivative of R squared with respect to R is going to be 2R, and then L minus 1 in the denominator, it is a constant that will be unchanged. So the derivative with respect to R is going to be 2R over L minus 1, which means that the inverse of this function is going to be dr over ds equals L minus 1 over 2R. And then finally, if I replace this function here in addition to the PR of R in the equation that we had for calculating PS of S or PDF of S, we will end up with 1 over L minus 1 as we did before. So as you can see, it can be mathematically proven that having a transformation function like we defined will give us a histogram equalized output. So now that we saw how it works for the continuous case, let's just reformulate the equation for the discrete case. So there are some differences between probability for discrete values and probabilities like continuous function. So for discrete values, instead of probability densities and integrals, we have probabilities and summation. So let's just quickly review the definition of the normalized histogram. So let's just say we have an image which is of size m by n, so m number of rows and n number of columns, and based on that we can define the normalized histogram in this form. So the discrete transform function that we use instead of integral now uses a summation, but the concept is very much the same. So S subscript k equals T of Rk, which is equals to the L minus 1 as the constant, and the summation of the intensity values over the range from 0 to k. And if I plug this function here, this is going to be simplified to this form, L minus 1 over m multiplied by n, and the summation of the number of pixels that happen to have a certain intensity. So this procedure is called the histogram equalization or histogram linearization transform. So let's just see how it works in practice. So let's go for an example. We have an example of an image which is 64 by 64 pixels, and let's just say we are using 3 bits to represent the intensity values in this image. So when we have 3 bits, that means that L is going to be 2 to the power 3 or 8 possible intensity values. The range is from 0 to 7. So this is the table that shows the normalized histogram of the image. So the first column is basically the intensity values. The second column is the number of pixels with that specific intensity value. For example, with intensity value of 0, we have 790 pixels with that intensity. And finally, the last column shows the normalized histogram of the image. So now that we have this, let's just use the definition that we had for the intensity transformation. S of k equals L minus 1, the summation from 0 to k of p of r rj. So let's just plug these values to this equation and find S of k for k from 0 to L minus 1. So for the first term, we have S of 0 equals 7, which is L minus 1, multiplied by only p of r0. As you can see here, we are calculating this summation over a range. So if k is 0, we only have one term here. So it will be 7 multiplied by p of r0. So 7 multiplied by 0.19, which is equal to 133. For S of 1, we will have the summation of two terms because j changes from 0 to 1. So we not only we have the term for r0, but also we have the term for r1. So the end result will be 3.08. We can continue this until we get to k being 7. In that case, the final value will be 7 because we will have 7 here, and then the summation from j equals 0 to 7, which is basically the summation of the probabilities over the full range, which, as I discussed before, adds up to 1. So now if we do this transformation, we realize that we have started from an image with 8 intensity values, but they are all integers. But on the other hand, after the transformation, now we have 8 intensity values that are not integer. In fact, they are fractional numbers. So to be able to remedy this, we need to round up or down these numbers to their closest integer in order to have a digital image at the output too. So the next step would be to round these values for S to the closest integer value in the range 0 and 7. So 133 becomes 1, 3.08 becomes 3, 4.55 becomes 5, and so on and so forth. So now we have calculated the intensity values of the output image and basically the mapping from the input image to the output image. So if you look closely, Here we have basically the intensity value for the input image, and here we have the intensity value for the output image. So for example, here if we have an intensity value of 3 in the input image, that will be mapped to an intensity value of 6. If we have an intensity value of 6 in the input image, that will be mapped to the intensity value of 7 at the output image. So this is a graph of the input uh, normalized histogram. So as you can see, we have a relatively decaying curve, but the aim was to have a more uniform curve at the output. So based on the transformation function that we defined, this is the transformation function that we get. So for example, 0 will be mapped to 133 as it's shown here. 1 will be mapped to 3.08 and all the way to 7. But this is before rounding the values. After we round the values and draw the histogram, the normalized histogram of the output image, we have a histogram that looks more like this. So you might say, okay, this is not as uniform as we expected, because in the continuous case we were able to create a perfectly uniform histogram for the output image. But you need to realize that when we are working with continuous functions, there is infinite possible values that we can have for the function values. But on the other hand, when we are working with digital images, that is not the case. We have a limited number of values that we can have for the intensity, and they all must be integers. And you will see the effect when we were doing the rounding operation as well, that because of the rounding, there were several intensity uh, values that are mapped to single intensity. So for example, we have 5.67, which is mapped to 6, but also we have 6.23, which is also mapped to 6. And the same is true for intensity values that are mapped to 7 too. But the point here is that even though this might not be perfectly uniform, but in comparison to the initial one, it is more uniform. So it is much more closer to a uniform distribution. Because a histogram is an approximate PDF and no new intensity values are created in the process, it is very rare to get a perfectly flat histogram in practical application. And unlike the continuous case, it cannot be mathematically proved that the discrete histogram equalization results in a uniform histogram. And the main reason for that is the rounding operation that we did is nonlinear. But however, histogram equalization is a fully automatic technique, and it doesn't need any extra parameter to be defined. So the inverse transformation from S back to R can be defined in this form. Of course, this is not 100% possible at all in all cases, especially as you can see in the previous slide that since several input intensity values are mapped to one output intensity value, going back from this is not unique and the correspondence is not one-to-one. So this transformation satisfies the two initial conditions that we discussed only if all intensity levels are present in the input image. Or in another word, none of the histogram bins of the input image are empty. But again, this is not something that you can guarantee for all the images that you want to process. So to summarize, histogram equalization has the advantage of being automatic without the need for any parameters, and it's conceptually optimal, even though in uh, real life applications there might be some limitations. So now that we saw how histogram equalization works, let's just apply it to the uh, first few images that I showed you of images with low contrast. The first image is the uh, image with a very dark appearance, and as you remember, the intensity values in the histogram are located primarily in the dark region of the histogram. After applying the histogram equalization, we derived this curve 1 as for the transformation intensity transformation function, and the resulting histogram after equalization is this, which as you can see is much more uniform than the initial histogram that we had. It can be seen in the result of the histogram equalization that now the image has much more contrast. The same happens for the image that was much brighter. Again, after applying the histogram equalization, we have a much more uniform uh, histogram for the output image, and the contrast is also improved. For the low contrast image, in which the intensity values were only around a very narrow range in the intensity range that is possible, we basically see the same thing. But on the other hand, for the originally good contrast image, we don't see that much difference in the histogram equalized and the original image. As I said before, here you see the curves that we came up with for the intensity transformation function. So the first curve is for the dark image, the second curve is for the bright image, and the third curve is for the low contrast image that we have here. And finally, for the image that is high contrast to begin with, you see that the curve is very close to the identity line that we can draw from 0 to this corner. And the reason for that is that the image already had a very good contrast, so even after histogram equalization, the appearance of the image does not change significantly. So now let's talk about histogram matching or histogram specification. So as you saw, histogram equalization tries to produce a transformation function to generate an output image with a uniform histogram. But that is not always ideal or needed. What if you want to specify the shape of the histogram yourself? So that is the topic for histogram matching, which gives you the option to specify the shape of the histogram yourself. So again, let's just assume the continuous case, and then we go for the discrete case. So for the continuous case, let's just assume that we have an image, an input image with PDF shown as PR of R, that we want to transform to an image with PDF PZ of Z. So here PZ of Z is not uniform. The general idea of histogram matching is to use histogram equalization as an intermediate step for the process. So let's first assume S as a random variable that is defined using the same transformation function as we did for histogram equalization. So basically using this transformation function, we transform the input image with variable R to a histogram equalized image with variable S. Now let's do the same based on variable Z. So let's convert the output histogram that we want into a histogram equalized version using function g of z, but uh, with a similar definition. So for the uh, input image, what we do is that we use PR of R, and we use W as the variable of integration. For the output image, we use PZ of Z, and we use V as the variable of integration. So now that we have these two, we can combine them to find out what is going to be the transformation function from uh, the input image to the output image. So since S is defined to be a uniform distribution, these two equations can be considered as equal. So now we have G of Z equals S equals T of R. So now what we do is that we need to replace the value of Z based on S and then based on R. So from this side of the equation, Z is going to be inverse G function of S, and then S is T of R. So conceptually, uh, going from R to Z can be done by calculating this uh, combined transformation function. So we can summarize the procedure in these 4 steps. So first we obtain the P of R from the input image. Basically we calculate the normalized histogram of the input image. Then we use the specified PDF of the output image, PZ of Z, to obtain the transformation function G of Z to go from the output image to the histogram equalized image. Now in the third step we compute the inverse transformation Z equals G inverse of S, which is a mapping from S to Z. And finally we obtain the output image by first equalizing the input. Then for each pixel S in the equalized image we perform the inverse mapping to obtain the corresponding pixel in the output image. So as you can see, the procedure is much more complicated than the previous one, but as I said, if you consider the histogram equalization as an intermediate step, you see that by performing the histogram equalization on both the input histogram and the output histogram, now we get to a common ground, and then we can use inverse transformation of G to basically go fully from the input image to the output image. But in general, finding the analytical expression for inverse of G is not a trivial task. However, in the discrete case, this is not going to be a problem. So now let's see how we can do this for the discrete variables. So we reformulate the continuous case for the discrete case. So first we histogram equalize from the input image to variable S, and that is done by using this transformation function for all the values of k from 0 to L minus 1. Then similarly, given a specific value of S of k for a value of q, which also q changes from 0 and L minus 1, we find the histogram equalized version of the output histogram. After doing that, the desired value for z of q is computed from the inverse transform that is introduced here. In practice, there is no need to compute the inverse of g, since we have intensity values that are integer. It is simple to compute all the possible values of g using the second equation. So these values are rounded to their nearest integer value and stored in a lookup table, and then given a particular value of sk, we look for the closest match in the table. So to summarize, these are the 4 steps that we need to take for histogram matching for discrete images. First, we compute the histogram P of PR of R of the input image, and then we histogram equalize it to the uniform histogram. Again, we round the resulting values to the integer values within the range. Then we compute all values of function g of zq. Basically, we histogram equalize the output histogram and round the values to integers in the range 0 to L minus 1 and store them in a lookup table. The third step is a bit more involved in comparison to the third step in the continuous case. So the main difference is that we may have multiple correspondence. So for every value of sk, for k from 0 to L minus 1, we use the stored value of g from step 2 to find the corresponding value of zq, so that g of zq is closest to s of k. When more than one value of zq gives the same match, so basically when we have multiple correspondence, by convention we use the uh, smallest value between all the matches. And finally, from the histogram specified image, we form the histogram specified image by mapping every equalized pixel with value sk to the corresponding pixel with value zq in the histogram specified image. And for that we use the mappings found in step 3. So now let's take a look at an example and see how this thing can be done. For this example, we use the exact same histogram that we use for the histogram equalization example. We have a 64 by 64 image which has 3 bits that represent the intensity values of the images. So in this table on the left we have the intensity values. The second column shows the number of times each intensity value appears in the image, and then the third column shows the normalized histogram, basically the probability of each intensity value happening in the image. For the output histogram, we are using these specialized values. So this column shows the intensity values for the output histogram, and these show the probabilities of each intensity value happening in the output. So here you can see the input histogram and output histogram as two figures. So as you can see in the input histogram we have a relatively decaying histogram, but on the output histogram, first of all, we don't have any instances of intensity 0, 1 and 2 happening, and the form is like a triangle for intensity values from 3 to 7. So let's just follow the procedure and see what is going to be the result of histogram matching. The first step was to compute the rounded histogram equalized values from the input image to a histogram equalized version of it. So this directly follows from the previous example. So we have S0 that resulted in 1.33, and then we round it to a value of 1. We have S1 which resulted to a value of 3.08, which we rounded to 3, and then so on and so forth. For the second step, we do the same for the output histogram. So we find the value for g of z0 to be 0, g of z1 to be 0, g of z2 to be 0, and if I go back one slide, you see that these three values are 0, so the summation over the range will also result in 0. And then you follow that for the rest of the intensity values as well. But again, since these values are fractional, but we cannot use fractional values, in digital images, we round these to their nearest integer values. So the first three will be rounded to a value of 0. Uh, then the fourth value is going to be rounded to 1, and then to 2, 5, 6, and 7. So now that we have these two mappings, then we need to find the mapping between sk and z of q. So the first three values of g are equal, so it's not strictly monotonic, therefore condition A prime is violated. But given this, we follow a step 3 of the histogram matching approach, which states we need to find the smallest value of zq so that the value of zq, g of zq, is closest to sk. And this is done for every value of sk to create the required mapping from S to Z. For example, for S0 being 1, we have G of Z3, which is 1, which is a perfect match, which means that every pixel in the histogram equalized image, histogram equalized input image with value 1 is mapped to a pixel with value 3 in the histogram specified image. But that is not all straightforward for other values, because we might have uh, multiple correspondence. And if you remember from the steps, by convention, when we have multiple correspondence, we use the smallest matching value. So after doing that, this is the matching that we come up with. So in the histogram equalized input image, any value that is 1 now is going to be matched to 3. Any value that is 3 is going to be matched to 4. Any value with value 5 is going to be matched to 5, 6 to 6, and finally 7 to 7. So as I said, the final step is to use the computed mapping to map every pixel in the histogram equalized input image into the corresponding pixel in the newly created histogram specified image. So after doing that, we can create the basically we can compute the new histogram of the image. This table, the middle column, shows the specified histogram that we aimed for, and the last column shows the actual probabilities that we got as the process of histogram matching. Of course, you can see it's not a perfect match, but if you look at the shape, you see that it's much more similar to the specified histogram than the input image was. And there are several reasons for that. First of all is that we have a relatively small image to begin with, and second of all is that we have regions that or like intensity values that basically do not appear in the input or in the output image. But overall, using histogram matching, we can define a specific histogram and try to match the histogram of our image into that specified histogram. Here is an example of how histogram matching and histogram equalization can produce different results. So on the left we have an input image, and underneath it we have the image of the histogram. As you can see, the image is very dark, but also it has very bright regions as well. But overall, the image is more dominated by dark and black regions. So now let's see how histogram equalization can improve this image. So the image in the middle is the result of histogram equalization. As you can see, the appearance of the image is much more brighter than the original one. There are some details that were not visible. For example, in this region, because of the very dark appearance, we cannot see some of the details, but in the histogram equalized version, it's much easier to see some of the details. but at the same time, as you can see, the image is very washed out and very bright. So because the dark regions are much more dominant in size in the image, the bright regions don't have that much of an effect in the histogram equalization process. So you can see the transformation function in this figure, that we have a very sudden jump right in the region that are very dark in the image. And as for the histogram equalized, the histogram is heavily shifted to the right. So the overall uh, histogram is now much more uniform, but at the same time, since we have a very large dark area within the image, the output of the histogram equalization is not ideal. On the other hand, uh, on the right we see the result of histogram matching. So when we look at the original image, we notice that the details in the bright regions are very much visible, but what is not visible, that effectively is the details inside the very dark region. So with the specified histogram, we try to basically stretch the uh, intensity values in the dark regions while we keep the intensity values in the bright region almost not affected. So as you can see here, this is the specified histogram that we use. As you can see, we are basically extending the histogram in uh, very dark region, while the bright regions are almost identical to the original image. So if we use this histogram, this is specified histogram, and the histogram matching, now we can get this result, which is much more pleasing than the first and the second images. Not only the features in both bright and dark regions are more visible, but at the same time the image has a more natural look instead of being all bright or look washed out. And here you see basically the estimated transformation function. This is the original transformation function from the S to Z, and this is the inverse of it. And then here you see the uh, histogram matched images histogram. Both histogram equalization and histogram matching are considered global histogram processing methods, since pixels are modified based on the intensity distribution of the entire image. So if you aim to enhance details over a very small region of the image, these two techniques fail because the number of pixels in those small areas have a very less significant impact in the uh, global histogram. So to remedy this, what we can do is that we can devise transformation based on intensity distributions of pixel neighborhoods. So in effect, we combine the single pixel operations with neighborhood operations to create local histogram processing techniques. For this, we define a neighborhood size, and then we move its center from pixel to pixel in a raster scanning manner. And at each location, we perform histogram equalization or histogram matching, and we find a new mapped intensity for the center pixel, and we replace the previous intensity with that new intensity value. One thing that you should notice is that this procedure is usually not done on the original image. In fact, a replica of the original image is created, and the processing will be done on that replica based on the values of the original image, because we are doing these processes pixel by pixel. If we basically change the values of the intensities for every neighborhood, since the neighborhoods are overlapping, we basically ruin the result of the processing. But one thing that you should know here is that since from every neighborhood operation to the next one, either one row or one column of the neighborhood changes, uh, especially when you have one pixel translation between neighborhood, you don't need to complete the full histogram for that neighborhood. What you can do is that you basically just update the previous histogram, so you are working with an updated histogram based on the calculation that is done for the histogram in the previous step. So let's just see an example of how this thing might work. So on the left we have an image which is a little bit noisy, but also it has these black regions that also contain some very faint uh, shapes inside of them. So other than this one, this circle, the rest of them, the shape of the uh, shape with a different intensity inside this black region is not that visible. So this is the result of applying histogram equalization in its local form. What you can see is that the noises are a little bit magnified and the image is a little bit washed out, much brighter than the previous one, but still the details inside these regions are not that visible, even though they are more visible than the original image. So if we do a local histogram local equalization with 3 by 3 neighborhoods, now you can see the details inside these dark regions much more effectively. Of course, this is only for you to see how these procedures can be done with whether globally or locally. For specific applications, the size of the neighborhood, the technique for each neighborhood can be defined differently at any other application. So now that we saw how we can perform contrast enhancement using mostly single pixel intensity transformation function, let's just talk about spatial filtering. So there are generally two components in any spatial filter definition. We have a neighborhood and then we have an operation that is defined on the neighborhood. So let's take a look at this image. So as you can see here, we have the image's origin, and then along the x direction we have the rows, and along the y direction we have the columns. So this image is divided into certain number of pixels. So as before, we have m rows and n columns. At any given point, we can define a neighborhood of a specific size, and this neighborhood has some weight associated with that. So as for the neighborhood, we define a different kernel or a mask that we move across this image pixel by pixel, and at any location we perform some operation. So as for the origin of the neighborhood or the kernel, we use the origin to be at the center pixel. So it is very common to use kernel of odd size in both dimensions, because if we are using kernel of even size in each dimension, we cannot define a center pixel properly. We can define a central point, but not necessarily a certain pixel. So here you see an example of a 3 by 3 neighborhood, and for each one of them, as I said before, we define a weight that is associated with that location in the kernel. So now let's say we apply this kernel onto this region of the image. So generally speaking, we can have two types of operations. we can either have linear operations or nonlinear operations. So linear operation, one example is averaging, and nonlinear operation, one example is median filtering, which I will talk about as later lectures. So linear spatial filtering usually performs a sum of product operation between an image F and a filter kernel, which we call here W. So the kernel, as I said before, is an array which defines the neighborhood of the operation, and its coefficients define the nature of the filter. So a kernel is usually also called a mask or a template or a window. So here you can see an example of a 3x3 kernel. For each location we have a weight, and also we have a coordinates which are defined based on the center of the kernel. So if at the center we have W of 0, 0, top left corner will be W of -1 and -1, and bottom right corner will be W of 1 and 1. So now let's just say we want to find the response of the image at any given location to the filter or to the kernel. So this is computed by the sum of product of the kernel coefficients and the image pixel encompassed by the kernel. So if we have this kernel and we put the center of this kernel at location X and Y, the response of the image to this kernel for that location, which we denoted here by G of X and Y, is going to be W -1 -1 multiplied by F of X minus 1 Y minus 1 plus W -1 0 multiplied by F of X minus 1 Y, and then all the way to W 1 and 1 multiplied by F of X plus 1 and Y plus 1. As we change the coordinates of X and Y, the center of the kernel moves from pixel to pixel and generates the final filtered image. So as I said, the center coefficient of the kernel W of 0, 0 always aligned with the pixel at the location X and Y. So we can make a more general form of this. As I said before, it's very common to use kernel sizes for which both the number of rows and the number of columns are odd numbers. So if we have that for a kernel size of m by n, lowercase m multiplied by lowercase n, and if both of these values are odd, we can define m to be 2a plus 1, for which a is a non-negative integer, and we can define n to be 2b plus 1. Again, b is a non-negative integer. So if we have that, we can reformulate the previous equation into this very nice form, in which g of xy is the summation over s changing from -a to a, and summation for t changing from -b to b of w of s and t, f of x plus s, and y plus t. So for the previous example, we had m and n to be both 3. So if we have that, the value of a is going to be 1, the value of b is going to be 1, and if we replace a and b as 1 in this equation, then we get to have the same equation. Of course, when we have kernels of larger sizes, it's much better to write the filtering operation in this form because it's much more concise. And as I said before, we change the values of x and y. Basically, we move the kernel from pixel to pixel across the image, and for each one of them we compute the response of that small neighborhood to the kernel, and based on those we can create the full filtered image. So the definition that I just gave you in the previous slide is the definition of correlation between two functions. So I repeated that definition here, but only for a one-dimensional function. So in the book, the correlation is shown by an empty star, but there is another common symbol for showing the correlation, which is a circle plus sign. So in the previous equation, if we assume that we are only having one variable, then it is going to be simplified to this equation. But in addition to correlation, we have another concept called convolution, which is usually showed by a black star or a circled multiplication sign, in which, as you can see, instead of finding the multiplication between ws and f of x plus 1, here we do the multiplication of w with f of x minus s. So you might say, okay, so by itself the change is not that significant. So let's look at an example to see how this slightly different formulation can produce some different properties. So to do that, let's just assume a kernel, a simple one-dimensional kernel, 1, 2, 4, 2, and 8. And let's just apply this kernel to a function f that looks like 0, 0, 0, 1, 0, 0, 0, 0. So this function is usually called a discrete unit impulse, and its definition in the discrete domain is like this. So delta of x minus 0 is 0 everywhere except where x equals x0. So for example, here if we assume the origin to be here and like we show this as location 0, then this function f is actually delta of x minus 3, because at location 3 its value is 1 and everywhere else its value is 0. So now let's just find the correlation between this function and this kernel. So first of all, for the kernel, we have its center to be the middle pixel here, so the center is 4. So first we put this kernel at the first location. So basically we align the center pixel at the first location of the function. But one thing that you might notice is that the value 1 and the value 2 basically fall outside the boundary of function f. So to avoid having undefined values, we usually zero extend the original function by some zeros either to the left or to the right. So since here we have two values that fall outside, we just put 2 zeros to the left, so now we don't have any undefined values. After doing this, what we do is that we find the element-wise multiplication between the kernel and the function, and we sum them all together. So 1 multiplied by 0 plus 2 multiplied by 0 plus 4 multiplied by 0 all the way to 8 multiplied by 0. And as you can imagine, the value will be 0. So this is the value, first value that we get. Then we move this kernel one step to the right, and now we are going to be in this position. So now if we find the element-wise multiplication and sum them all up together, we have 8 multiplied by 1 plus 2 multiplied by 0 all the way to 1 multiplied by 0. So the result of this is going to be 8. So this is the second element. We do it for the third element, the fourth element, all the way to the last element of the original function f. So if we do that, this is the correlation result that we get. So one thing that you notice is that the kernel, basically the correlation result is the reverse kernel at location for which f is 1. So now let's see what happens for the convolution. The effect of having this formulation is similar to basically pre-rotating the kernel 180 degrees and then applying the same correlation procedure. So for convolution, we pre-rotate this 180 degrees. So instead of having 1, 2, 4, 2, 8, now we have 8, 2, 4, 2, 1. Then place its center at the first location. Again, since we have two values which fall outside the boundaries of f, we add two zeros. Basically, we zero pad the original image, and then we again find the uh, element-wise multiplication and then sum the result. So for the first one, the result is going to be 0. If we move this one step to the right, now we have the result of 1, and then 2, and then 4, and then 2, and then 8. So one thing that you might notice is that when we pre-rotate the original kernel, now for the result of convolution, we basically have an original replica of the kernel at the location where the original image had the value of 1, or basically the discrete unit impulse had the value of 1. And that is something that is very useful in practice. So again, pre-rotating the kernel results in an exact copy of the kernel. So in effect, we can say linear spatial filtering and spatial convolution are synonymous. But this was only for a one-dimensional case. Let's just see what happens for a two-dimensional case. For the two-dimensional case, this is the exact same definition that we had in the previous slide. So we have the summations from negative a to a and negative b to b over the two variables of the function. For the convolution, we have the variables of summation to be basically inverted, or like with negative sign. So let's see what is the effect in both correlation and convolution. So since we are working with two-dimensional functions, now the original image is all zeros with 1 at the center, and the kernel that we have is a 3x3 kernel with values 1 all the way to 9. Again, since we want to avoid any undefined values, we zero pad this data. So in the previous case, what we did was we zero padded along the only one axis that we had, since it was a one-dimensional signal. But now, since it's two-dimensional, we zero padded both along the horizontal and vertical direction. For the correlation, again, we place the center of the kernel at the first pixel of the image, right? Basically, this is the first pixel of the image, and this is basically after zero padding, right? So what we do is that we find the element-wise multiplication between the element of the kernel and the pixel values of the original image, and then we sum them together. So if we do this for this location first, we get the value of 0, which is here. If we move it 1 pixel to the right, again we get 0, 1 pixel to the right, 0, and then all the way until the last element of the first row. Then we move this 1 pixel to the one pixel down, and then we do the same. So after repeating this process for all the pixels in the original image, this is the correlation result that we get. And as you can see, in comparison to the original kernel, this is reversed in both horizontal and vertical direction. So now for the convolution, what we do is that we basically flip the original kernel in both horizontal and vertical direction and repeat the correlation process. So this is a view of the rotated or like flipped kernel in both horizontal and vertical directions. And after doing the correlation of the image with this kernel, this is the result that we get. And as you can see, basically we have exactly the same kernel at the location for which the value of function f is 1. So again, pre-rotating the kernel results in an exact copy of the kernel. And again, for 2D cases, linear spatial filtering and spatial convolution are considered to be synonymous. So even though you might say the difference between correlation and convolution is not that significant, and it's only you basically get the exact same result if you flip the kernel along both horizontal and vertical direction. But when you talk about more advanced filtering procedures that are done in image processing, uh, going with convolution instead of correlation has a lot of benefits. To go over those, let's just see what are the properties of convolution and correlation. So for the first property, for convolution, we have the commutative property, which basically means that convolution of f and g is equal to the convolution of g and f. But we cannot say the same thing for correlation. So correlation of f and g is not the same as correlation of g and f. So because of this nice property of the convolution, it doesn't matter whether we pre-rotate the kernel or the image, we always get the same result. But for the correlation, it's different if we find the correlation between the image and the kernel or from the kernel and the image. There is another property which is called the associative property, which basically says that the correlation of the convolution of f and the result of convolution of g and h is equals to the convolution of f and g convolved with the function h. So as you can see, basically it doesn't matter whether we first find the convolution of f and g and then convolve the result with h, or if we calculate the convolution of g and h first and then convolve the result with f. But again, we cannot say the same thing about the correlation. And finally, we have the distributive property, which is common in both correlation and convolution, which basically says that we can distribute the convolution and correlation over summation. So because of the commutative property of convolution, as I said, it is not important whether the kernel or the image is pre-rotated. Also, and this is a very useful feature, is that when we have multiple stages of filtering, it is very useful to use this commutative and associative properties, because what we can do is that we can first convolve all the filter kernels first and then convolve the result with the image. So in terms of final result, it doesn't make any difference, but we cannot say the same thing about correlation. So the takeaway message is that spatial filtering is always done using convolution instead of correlation. Of course, there are some cases that you can interchange these, especially for deep learning applications, but that is a topic that probably will be covered by the end of the course. So now let's talk about separable filter kernels. If you remember, when I was talking about converting an image to a transform domain, for example, going from a spatial domain to frequency domain, I talked a little bit about separable kernels. So generally speaking, a 2D function g of xy is said to be separable if it can be written as the product of two 1D functions. So g of x multiplied by g1 of x multiplied by g2 of y. So for example, let's just say we have this kernel. We say that it is separable because we can write it as the form of multiplication of C and R, right? So we multiply C in its original form with the transpose of R, and if we do that, we get exactly the same kernel. So if we have a separable kernel size of lowercase m by lowercase n, we can express it as the outer product of two vectors v and w, so in which v has m rows and one column, and w has n rows and one column. If the kernel is a square, basically has the same number of rows and columns, in that case uh, it can be even simplified to uh, only needing to know one kernel, basically one of the kernels, and then if we multiply the kernel with its transpose, we get the original separable kernel. So this outer product that we define here is basically equivalent to the 2D convolution of a column vector and a row vector. So now let's see how this equivalency is beneficial to us. So do you remember we said that the convolution has some nice properties? We had the commutative property. Basically, we can interchange the location of the function when we perform convolution, and then we had the associated property, which basically said that the order of the convolution is not important when you have more than one convolution. So now if we have that, let's just say we have a separable kernel called W, and we want to find the convolution between W and F. So now, since W is separable, and since we said that the outer product that we define here, so whether the kernel is a rectangular kernel or like is a square kernel, it doesn't matter. This outer product is equivalent to convolution. So now that means that we can write W in terms of W1 convolved with W2. So if we use the commutative and associative properties, we can see that W convolved with F equals W1 convolved with F, and the result of this calculation is convolved with W2. So now, why is this important? It is important because it means that if we have a separable kernel, we can basically reduce the number of calculations that we need to do in order to find the filtered result. So generally speaking, the computational advantage of a separable kernel in comparison to a non-separable kernel in terms of the number of multiplications and summations can be derived as this ratio. So if the kernel is non-separable, we have to have m by n by m by n number of calculations, multiplications and addition. But if it's separable, this number is reduced significantly. So the ratio between the two is basically gives us the amount of advantage that we get if we perform the convolution in a separable way. So for example, if our kernel of size 11 by 11, just this simple change gives us 5.5 times boost in terms of computational performance. It's even higher for kernels of larger size. So for example, if our kernel is 101 by 101, it gives us more than 50 times advantage. So now that we learned this, let's just see how we can create separable kernels based on a kernel. So to do that, first we need to verify if the kernel is separable to begin with. So usually the matrices that are formed by a product of a column vector and a row vector always have a rank of 1. So in another word, rows and columns of such matrices are linearly independent, meaning that the rows only differ by a constant multiplier, and again, columns are only different by a constant multiplier. But how can we, if we are given a kernel, how can we see if the rank is 1 or not? So the mathematical derivation of the equation is out of the scope of this course. For us, since we only care about the rank and not necessarily how this rank is calculated, I suggest you take a look at the rank function in MATLAB. So you will give a matrix to this function and it provides the rank of uh, the matrix. So if you are given a matrix or a kernel that you know that you want to see if you can represent it as a separable uh, set of kernels, first you use the rank function to determine if the rank is 1 or not. If the rank is 1, then you follow this three-step process to basically come up with the separable kernels. First, you find any non-zero element in the matrix and you denote its value as E. So this can be any non-zero element in the matrix, not necessarily the first one or the last one. After you select that non-zero element, then you form two vectors, C and R, equal to the column and row in the kernel that contain that exact element. So after doing that, then you can define the two separable kernels V and W transpose as V being equal to the column vector that contains element E and W transpose as the row vector divided by E. Uh, Basically the row vector that contains E divided by E. And just by doing this simple transformation for any kernel that has a rank of 1, you can come up with two separable one-dimensional kernels which you can convolve with your image in any order you want, and overall the um, computational complexity is going to be much less than if you basically convolve the original kernel with the image. Since in the next lecture I'm going to talk more about different spatial filtering that we can have, and a lot of the concept can be better represented in the frequency domain. Let's just briefly go over some of the useful properties of frequency domain. Of course, more consideration and more discussions of these properties will be done in chapter 4 of the book. So as you know, Fourier transform is used to go from the spatial domain to frequency domain. So in effect, Fourier transform decomposes the signal, or here the image, into its frequency component. So there are two fundamental properties that you need to consider. First of all, is in terms of the convolution. So convolution in the spatial domain is equivalent to element-wise multiplication in the frequency domain and vice versa. So that means that if you want to find the uh, response of an image to a kernel in the spatial domain, you have to find the convolution between the image and the kernel. But in the frequency domain, what you need to do is that first find the frequency or Fourier transform of the kernel and the image, and then in the frequency domain you just simply calculate the element-wise multiplication. And the same goes for other way too. So if you have a convolution in the frequency domain, that is equivalent to multiplication in the spatial domain. And the second fundamental property is that if we have an impulse function of amplitude A in the spatial domain, it is going to be a constant function of value A in the frequency domain and vice versa. So here you can see an example of a filter that is defined in the frequency domain. So considering U as the frequency and the vertical line as the amplitude in any frequency, in this region, whatever frequency we have in this region will get a value of 1. That means that it will be passed to the final result, but anywhere here will be stopped because the amplitude is going to be 0. And its spatial equivalent looks like this. Of course, this is beyond what I want to cover in this lecture. We will see more specific when we talk about frequency transform or Fourier transform. But it is useful to know how we usually build a spatial filter. So there are 3 main approaches for building spatial filters. One is by formulating based on mathematical properties. So for example, we can use integration or averaging for blurring an image, or we can design spatial filters which compute the local derivatives to sharpen or enhance the edges of an image. The other way is by sampling a 2D spatial function for which the shape has a desired property. So for example, we can create a weighted average filter by sampling a 2D Gaussian function. Or we can sample the inverse Fourier transform of a 2D filter that is specified in the frequency domain. And finally, we can design a spatial filter with a specified frequency response. For example, designing a 1D spatial filter and then forming a separable or like circularly symmetric 2D version of that. Of course, we will see more examples of these in the upcoming lecture. So in the next lecture, I will talk about smoothing low-pass spatial filters, sharpening high-pass spatial filters, then high-pass, band reject, and band-pass filters designed based on the low-pass filters, and finally how we can combine different spatial enhancement methods that we talked so far to improve the appearance of images.